this chapter is actually, I mean, it's got a lot of new material. It's not super hard. There are especially the MPLS section. It does kind of get a little complicated for a little bit, but overall, I think this chapter is fairly average as far as difficulty, but actually kind of interesting. So we're talking about VRFs, MPLS, and MPLS VPNs. So we'll start by talking about VRF Lite. So VRF stands for Virtual Routing and Forwarding, okay? And that basically, it's like the equivalent of VLANs only for routers, where we're creating separate routers out of a single physical one, okay? So basically you've got interfaces, routing tables, and forwarding tables that are going to be isolated depending on what VRF instance they're associated with. And traffic from one VRF instance cannot interact with another on that same device, okay? So, and this then will end up leading up to an MPLS layer 3 VPN architecture. And I'll talk about what that is. It doesn't necessarily involve anything like encryption and stuff like that. It's a virtual network on top of a separate physical network. It's not about encryption or anything. All right, so essentially what this does is increase router functionality through segmentation in lieu of using multiple devices, right? We're basically chunking up a physical network into several other underlying, well, overlaying networks, instead of actually buying the equipment we would need to create multiple physical networks, okay? VRF Lite is what we call VRF, but without MPLS, okay? So you have a global VRF instance. All of your interfaces, everything kind of belongs to that by default. That's basically the routing table you have been working with, the global VRF instance, okay? But you can divide everything up into different instances and basically creating separate routing tables, okay? And of course, the obvious question is, why would you do this? We kind of talked about it already. One of which is security reasons. Like, you want to build multiple networks and the traffic needs to be isolated from other networks, okay? Or maybe, you want to do this, but then you only want to build one single physical network while still accommodating these separate networks, possibly for money, right? It's cheaper to do this. Okay, so here's an example where we have one physical topology, but 3 separate networks, right? So we've got the red network on top, the 10 dot space, the green network going in the middle, like PC2 to PC5, and the blue network across the bottom in 192.168 space, okay? Now, I just kind of want to point out, because this is, you'll notice, like, right there, we have sub interfaces right here. This is just one physical connection, okay? Because we're going to look at the configuration for this. So, like, for example, R1, we've got 3 physical interfaces over here. Here, this is one physical interface, but 3 sub interfaces, all right? R2 is going to have a total of 6 sub interfaces. R3 is going to have 3 sub interfaces with 3 physical interfaces. Okay, so just kind of keep that in your mind as we're talking about how we're going to configure this. First thing we're going to do is create the VRF instances. All right, so this is like almost like creating a VLAN on a switch. Okay, so IPVRF red, and pretty much everything that we do here has an IPv6 equivalent. All right, so we're not going to bother going through both sets of commands. It's basically the same. The IP addresses look different, and that's the only difference. All right. So we can see on R1 we have the VRFs existing. All they do is exist. You can't do anything with them yet. All right. So we're going to assign the interfaces to the appropriate VRFs. the physical interfaces anyway. Don't forget R1 is going to have 3 physical and 3 sub interfaces. All right, so we've got the 3 physical interfaces assigned. Let's verify that. This is just like doing a show VLAN, right, at layer 2 on a switch. So we can see each VRF has a physical interface. Now these used to belong to the default VRF, right? But now they belong to the ones listed here. Okay, one interface can belong to one VRF only. So if you need more, that's why we're going to use sub interfaces. Okay, so now on R1 we're going to create these sub interfaces and then assign them to the VRF. Okay, so gigabit 3.0 is the physical interface, but then we're going to have sub interfaces .1, .2, and .3, and we're going to assign them to the appropriate VRF. Okay, now once we do that, we can verify that with the show IP VRF command again. And now we can see blue has 2 interfaces, right? Gig 2.0 and gig 3.0.3. All right. Same thing with green and red. They each have a physical interface, right? And a sub interface. And now to put IP addresses on them and whatnot, it's the same like you would normally. Okay, so on the physical interfaces, we just IP address, no biggie. On the sub interface, we gotta, we're doing, it's basically kind of trunking, right? So we gotta tell it what VLAN it's going to be a part of. Okay, so we're just using 100, 200, 300, and then assign it the appropriate IP address. Now we do show IP VRF instances on R1. Now, I'm sorry, interfaces, not instances. Now we can see each interface, its IP address, and the VRF it belongs to, and if it's up or down at layer 3. So, by creating these VRF instances, we're essentially creating virtual networks, a network within a physical network. Each of these virtual networks has its own routing table, and thereby comes our isolation. They can't interact. All right. So again, as a reminder, to create the VRF, you just do IP VRF and then the name of it. All right. At that point in time, a routing table is created for it. So if you remember to look at the global routing table, you do show IP route. Okay. So we're doing this on R1 and we can see it's empty. All right. If we need to do this but for a VRF, that's going to go right here. Okay. So we're going to do show IP route VRF red. And then it tells you routing table red. And then it gives you the actual routing table. And we saw that the red network was the 10 dot. Okay. If we look at the green, and we got 172.16. Okay. And then same thing with the blue network, but that one's 192.168. Okay. All right. So that's R1. Now we got to configure R2. Before we get to R2, any questions or anything? All right. So create the VRFs, step 1. Then we're going to go to each interface and assign it a VRF. All right. Now we did that kind of in 2 separate steps, but we're going to do it all at once here. So we assign gig 30.1 to red, and R2 is all sub interfaces. Okay, so we got to do the encapsulation IP address. Then we're going to do .2 green encapsulation IP address. All right, and so we're going to do that for a total of 6 sub interfaces for R2. So if we do show IP VRF interface, here we can see all 6 sub interfaces. Okay, so we got gig 2, gig and gig 3, each, .1, .2, and .3. Okay, And of course, the way we subnetted it, this is connecting routers 1 and 2. That's connecting 2 and 3, 1 and 2, 2 and 3, 1 and 2, 2 and 3. And this is router 2, so it's dot 2 all the way down. Okay. Now let's take a look at the routing table. Show IP route VRF red. We can see there's the 10, right? We can see green with the 172.16 and blue 192.168. Okay. So that's R2. Now we're not going to go through all the commands for R3. It's very similar, right? Except R3 is going to have 3 sub interfaces and 3 physical ones, just like R1 did. Okay. So ping, super useful command. But now if you just issue the ping command, this is what it looks like. Now we're doing this on R1. We can see it didn't work. Why? Because we have to specify the VRF instance. The global routing table is assumed, and of course we saw there's nothing there. Okay. Now we're going to ping green. Oh, this one didn't work either. Well, that's because the 10 dot is the red space, right? It's the red network. And the two VRFs cannot interact. So the green VRF cannot ping anything in the red VRF. So now we're going to specify the correct VRF and the correct IP address, and we can see that it works. Okay? Because we're pinging the 10 dot space, so we need to be red. So if we look at the routing table in R1, again, there's the 10 dot space, red. Okay. But notice this is just connected and local routes only. So let's configure some routing, okay? So we're going to go into named configuration mode for EIGRP. So we're going to say router EIGRP VRF example. Okay, so do you have to specify the VRF instance with the show IP route VRF command, or can you just use it alone to see all of the VRF routes? You know what? I have seen it both ways. I think that's a function of the iOS version. So it'd be interesting to try that on the labs to see if that's supported on those routers. That's a good question. It could go either way. I don't generally, most of the time, if you're in an environment that's using VRFs, you're going to have a pretty decent routing table, right? And so doing a show IP route VRF without specifying the specific VRF is just going to give you a lot of output. 99 times out of 100, you're dealing with a specific VRF, and that's all you want to look at. So that's usually what you have to do. But, I'm sure there's a use case for just having it kind of list all of them. Good question. All right, so at this point, we're in named configuration mode. Now we need to specify the address family. Okay, so we have 2 address families, IPv4 and IPv6, but it's actually the layer 3 protocol and the VRF. By default, it's the global VRF, so you don't specify it, right? So in this case, we're going to specify the red VRF, and we're going to say autonomous system 10 to kind of go along with the address space that we're working with, okay? Then we're going to do the address family IPv4 for the green VRF, and we're going to use autonomous system 172 for that address space. And then the same for blue, we're going to use autonomous system 192 for that address space. Okay. So now let's take a look and see what interfaces are participating in EIGRP. Now to do this, again, you have to specify the VRF that you're concerned about, all right? So here, we're going to look at the red VRF, and we can see we've got one physical and one sub interface, which makes sense for R1. We specify green, same thing, okay? And you can see autonomous system 10, autonomous system 172 for the red and the green, all right? We're going to assume blue is good as well, and just kind of go on. Now we could do show IP EIGRP, right, neighbors with the VRF inserted right after EIGRP. Okay, the VRF kind of tacks on to the EIGRP, so show IP EIGRP neighbors becomes show IP EIGRP VRF red neighbors. So hopefully that'll pointing that out will help you remember that it doesn't go over here in the end. It's attached to EIGRP. Okay, it's like you're going from big to small, right? The layer 3 protocol, the routing protocol, then the which routing table, and then the specific command, the neighbors part. Okay, so the scope is getting smaller as you progress through the command. All right, so we can see R1 has one neighbor, which makes sense, right? Because the layout is R1, whoops, R1, R2, R3, right? So R2 would have two neighbors, but R1's only going to have one. So we've got the green VRF, right? Autonomous System 172, one neighbor. Okay, so that's VRFs in a nutshell. Any other questions? Actually, I think this lecture is going to be a little bit shorter than I anticipated. We're almost half done, believe it or not. All right, the MPLS and the MPLS VPN section will be a little
maybe
bit slower.
you're going very fast.
Okay, okay. All right, so MPLS. So we'll start with MPLS, and then we will talk about how to do MPLS with the multiple VRFs in order to create an MPLS VPN, which is more of a service provider thing. Okay, so multi-protocol label switching, or MPLS. Okay, this is a packet forwarding method. All right, and it makes forwarding decisions, but it does that using these labels. Okay. We're not using any layer 3 packet destination. And part of the reason behind that is the multi-protocol aspect. All right. MPLS can be used to shuffle layer 3 packets, IPv4 packets at layer 3, IPv6 packets at layer 3. You can do frames, Ethernet frames at layer 2. It doesn't care because it can switch or route, depending on how you want to think of it, multiple protocols. It doesn't care because it's not making a decision based on the address of that protocol. It is using labels instead. And the reason why this is so useful for a service provider is it can have a MPLS network, and it can, like if you have a, so you got a service provider. So you have a service provider network, right? And you've got a branch here and a branch here. And you want like Metro Ethernet, right? Pseudo wire. So actually, so those are your provider routers, and the path can take whatever. But you essentially want it to be something like this, where you have an Ethernet cable that is plugged in. That's supposed to be an end of an Ethernet cable. And it's a 1,000-mile long Ethernet cable, and then it just kind of plugs in here. And so a frame goes here, and it gets spit out over here. All right? And so the service provider network just has this frame. Okay? The destination of a frame is a MAC address. How the heck do you route a MAC address through a service provider network? Okay, well, we don't. Basically, these service provider routers know that we have a layer 2. That's why it's frames going across a layer 2 VPN tunnel from the service provider router on the left to the one on the right. And so it's going to attach a label to that frame. And the label is going to be used for making routing decisions in order to get it across the service provider network. So the nice thing about MPLS is it doesn't care. It's multi-protocol label switching. Okay. So it's not going to use the layer 3 packet destination. Um, Supports many layer 3 well, and layer 2 as well. Okay. It's not a lot faster than just regular IP routing, you know, but why use it? Well, if you have your service provider routers and say they're routing lots of different things, okay, lots of different protocols, different customer routes. All right, this simplifies it. We can forward that all across a single network, regardless of what we're forwarding, whether it be frames or IPv3 packets, IPv4 packets. It doesn't matter. Okay, so let's talk about the router itself and how it works. All right, so we have a label switching router, or LSR. Okay, it's divided up into a control plane and a data plane. I mean, there's a management plane too, but we're not really concerned with that right now. Okay, in the control plane, we have the routing protocol and the label distribution protocol. All right, so the routing protocol is going to exchange routing information with other routers. Okay, and it's going to take the information that it learns and it's going to put it in the IP routing table. Well, the label distribution protocol is going to exchange label information with other MPLS routers, and that is going to populate the label information base, just like the routing protocol populated the routing information base, or the routing table. Okay, so that's the routing table is the RIB, routing information base. The label table, I guess you could call it, is the label information base. Okay, so that's at the control plane. Now that needs to populate the data plane. All right, so the IP routing table populates the forwarding table in hardware. Right, so if you remember from our discussion from 240, you've got the in switches, and that's why these are called, it's called MPLS switching, because it's done in hardware. Um, the routing table is pushed down into the forwarding information base, so it goes from the control plane, which is CPU, to data plane, which is specialized hardware, not general purpose like CPU. Okay, so the the routing protocol populates the routing table, which then populates the forwarding table. Okay, the label distribution protocol populates the label information base, and then that is going to populate the IP forwarding table and the label forwarding table, both depending. Okay. Then the label forwarding table can then inform the forwarding information base. Okay. So an incoming packet comes in. This one happens to be unlabeled. It's an IP packet. All right. Well, if there's no labels, we can't use the label forwarding table. We're going to use the IP forwarding table to send it on its way. All right. But if we have an incoming packet that is labeled, well, depending on the situation, that could go out labeled or it can go out unlabeled. Now, unlabeled basically means, in order for it to do something like this, that means this is the last label switch router. And the next router is a customer router that doesn't do MPLS. So we're going to take the label off. We're going to forward it to the customer router without the label on it. All right. Otherwise, it's going to go with the label and continue on as a labeled packet. All right. Does that make sense? Are you picking up what I'm putting down? All right. Thank you. Okay, so here's an example. We have the MPLS domain that's kind of shaded there. All right, so we're going to use some label switching routers. And again, what's an LSR? It's just a router that supports MPLS. It understands MPLS labels. It can send and receive labeled packets or labeled whatever, frames, whatever we're doing. Okay, in this context, we're talking about a layer 3 MPLS implementation, but it can be, layer 2. Okay, so the MPLS domain is R1 through R5. R1 and R5, half of it's in the MPLS domain and half of it's not. Okay, so we have an edge LSR that's at the edge of the MPLS domain. All right, so it's going to be known as an ingress LSR if it's receiving unlabeled packets and then adds a label to it so that that packet can enter the MPLS domain. On the other hand, if it's getting labeled packets that are then going to, leave the MPLS domain, it's going to remove the label and send the packet on its way, right? That's the situation over here where it comes in labeled, but then it comes out here and goes unlabeled. Okay, and then of course you've got intermediate LSRs that are going to be in the middle of the MPLS domain. And of course, these are pretty much just going to look at the labels, okay, because they're not adding or taking off any labels. So that's all they're going to be looking at. So the packet's going to go along this path, okay. The label switched path is the sequence of routers, okay, that it's going to travel through the MPLS domain. Now, the LSP, the path, it's a unidirectional path. All right, so source to destination. That's different for the returning traffic. Okay, now the returning path may be the exact same path in reverse, but that's not guaranteed. It could be just another path altogether. Okay. So a lot of times it's the same because of the underlying routing protocols used to build these paths. But again, that's not always guaranteed. Okay. So here we have a situation. We have a label switch path from R1, okay, to R5 to reach the 10.000/24. All right. So along that path, each router is going to take a look at the label, make its forwarding decision, remove the label and add a new label if required, and then forward it. Okay. So for R1, to get to the 10 dot network, the destination, it's going to add label 87, which goes out R2. Okay. Once it gets to R2, it's going to have an inbound label of 87. That tells R2, okay, that means we need to relabel it 11, send it to R3. R3, it sees it coming in labeled 11, and it knows, oh, I need to relabel it 65 and send it R4, so on and so forth. Okay. Over here, R5, it's going to see it coming in with a label of 23. There is no out label, so it's going to do it via the forwarding information base, which basically means it's going to make a routing decision based on the IP address and then forward the packet. Okay, so what is that label? All right, well, we call it a shim header because it just kind of gets put in there. All right. So since we're talking about packets, this is what's being carried. All right. It's going to go in between the IP header and the frame header here. We've got one, two. Well, actually, hold on. The label itself has 4 different fields. Okay, so it's 32 bits in total, divided into 4 fields. The first one is the actual label itself that identifies it. It's 20 bits. Okay. Then we have the next field, which is 3 bits, and It's used for quality of service purposes. Okay, originally that was labeled experimental, but now it's used for quality of service. Then we have the S bit, which just basically indicates if it is the last label in the stack. So if multiple labels are used in the packet, is this the last label? So this whole entire label could be put in multiple times. If I go back here, you might there are cases where you could have more than one label. All right, we're not going to get into that, but just know that that's the possible. Okay, and so this basically just says, is this the last label or not? Okay, and then we have a TTL. All right, so obviously if it reaches 0, you're done. Okay, so remember LSR is label switched router. So a MPLS router assigns a label, okay, so that's this part, the label number, to every network that they know about. Okay, how does it know about a network? It could be locally configured, like an IP address on an interface. All right, it could learn about it via dynamic routing protocol. All right. So each router assigns a network that it knows about a label, a locally assigned label. Okay, it needs to then advertise that to the other routers via what's called label distribution protocol. All right, so if an MPLS is enabled on an interface, okay, then we have label distribution hello packets that are going to get sent. All right, so it's sent to 224.0.0.2. That's the all routers multicast address. Okay, it's sent via UDP 646. All right, now once a router receives a hello packet, we're going to kind of make a transition from just UDP, which is just kind of thrown out there, to actually forming a TCP connection between the two routers. All right. So now we're going to form a TCP connection on port 646. So at least the port numbers remain the same. We're just going to switch from UDP to TCP, so you don't have to try and remember two different port numbers. All right. Now at this point, we can actually exchange label information. Okay. Now we have an LDP ID, Label Distribution Protocol ID. All right. That's going to uniquely identify the neighbor. And this ID is per interface. Okay, so we're going to send a different label out each interface for a single network. All right, so like for example, a label for the 10 dot network that we were just talking about. And I'll show you an example of this in just a second. All right. During this TCP process, one router is the active router, and it's the one that is responsible for setting up the TCP session. The higher the LDP ID, that's the one that's going to be the active router. Okay. So again, here's the MPLS domain. All right, and so we've set up the TCP session. All right. And R1 is talking to R2. So R1 is going to, so it picked label 19 for the 10 dot network, right? That's why it's local. That's its ID number for 19. R2 picked 87 for the 10 dot network. Okay. And so R3 picked 11. R4 picked 65, okay. R5 picked 23 for the 10 dot network. All right. So now they need to advertise that, right? So R2 advertises 87 belonging to the 10 dot network. So now R1 knows if it needs to send that to R2, it needs to label it as 87. Okay. Whereas R1 advertised 19, so that if R2 were to send a packet to the 10 dot network via R1, okay, R1, it would have to label it as 19. Now we can see that's never going to happen, right? R2 is never going to send it to that network that way, right? If we're trying to get to this network, R2 is only going to go that way, so to R3. But it knows that if it needs to send it to R3, it needs to relabel it 11. Okay, so let's take a look at R3. All right, so that's so again, R3 picked 11 for the 10 dot network. That is the locally significant label. It needs to let its neighboring routers, R2 and R4, know about 11 is for the 10 dot network if you want R3 to handle it. Okay. So R3 also knows that, again, if it were to send a packet via R2 to get to the 10 dot network, it would need to label it as R7. Alternatively, it would need to label it as 65 for R4. Okay. So all of these populate the label information base, right? So this is the label information base. Okay. So now we kind of, based on the information in the IP routing table, the routers have populated the label forwarding information base as appropriate. Okay, so this is the entire label information base for the 10 dot network. But if we're actually going to send something to the 10 dot network, it's going to come in from somewhere, either side. It's going to come in labeled as 11, right? Because R2 and R4 know that if they're going to send something to the 10 dot network to R3, they need to label it as 11. All right. So R3 knows, oh, label 11 means it goes to the 10 dot network. All right. Well, I happen to know, based on my IP routing table, I've figured this out ahead of time, that I need to go via R4. All right. So the R4 information then comes down here. And we're not going to worry about that, the R2 information. So regardless of where it comes in at, if it's labeled as 11, we need to change it to 65 and send it out the R4 interface. Okay. Now, this all happens. It gets to R5. Okay, so R5 gets the packet for the 10 dot network. It has a label. Okay, it has to look at the label forwarding information base, and so it comes in as 23. All right. However, we're not going to send it out labeled. There's no further LSRs. So it's got to remove the label, then look at the destination IP. We're going to do a second lookup in the forwarding information base. This isn't efficient, all right? It's a waste of time. So we do have a solution for that. It's called the penultimate hopping. Okay? Basically what that means is R4 removes the label when it sends it to R5 so that it is not labeled. Since it's not labeled, R4 knows that R5 is the last hop. It'll come in with just an IP address. So R5 won't waste time with the label lookup. It'll just look up in the IP address, do an IP routing decision, and know, okay, it gets sent out there. Okay? So that's core, the basic foundation of MPLS, how that works. Anybody confused about anything in that process? Now, again, with this certification, Cisco wants you to have a rough understanding of MPLS. You are not expected to configure it, utilize it, troubleshoot it. All right. As a matter of fact, there's not any labs for this chapter. So don't feel like you have to be an expert. Just Cisco just wants you to have a familiarity with it. Now, if this were the service provider cert track, then yeah, MPLS would be a lot more important. But this is just enterprise routing and switching. And since enterprises deal with service providers that use MPLS, it's helpful for the enterprise customers to have a basic understanding of what MPLS is, even though you're never going to see it or configure it or anything. It's all behind the scenes on the service provider side. Okay. Now that we have a rough understanding of MPLS, now let's combine that with the whole VRF, right? Virtual routing and forwarding, where we're separating the different routing domains and then having MPLS work with that. We saw how that worked with EIGRP. Now let's see how that works with MPLS. So we get into the concept of an MPLS VPN, again, virtual private network. It looks like it's its own little unique network on the hardware, but the hardware itself is carrying multiple of those. All right, so again, don't confuse this with like an IPsec VPN or something like that. There's no encryption inherent in this. That would have to be handled at the application layer or separately between the two customer routers. Okay, so here we have the MPLS domain, which we are also now going to call the P network or the provider network. Okay, and then over here we've got the customer network. Okay, so we have customer A, and this is customer A, site 1, site 2. Okay, and then we've got customer B, site 1, site 2. Okay, so MPLS layer 3 VPNs. So we have peer-to-peer connectivity between private customer sites across a shared network. All right, so this shared network is the ISP network that multiple customers are being able to allow to use. All right, so we basically have an MPLS VPN tunnel going here and going across there. Okay, so let's talk about how this is set up. So we have the customer network, which interfaces with the service provider network or the P network using CE routers or customer edge routers. The customer edge routers do not understand MPLS and they don't see it. They have no knowledge of it. They have no knowledge of VRF instances. Okay, so this way the whole MPLS thing is hidden from the customers. They don't care about it. The provider edge routers do all of the magic. Okay, those are the ingress and the egress LSRs or label switch routers for the MPLS domain. All right, they are also known as P routers or provider routers. Right, so basically what we're trying to do is the customer sites are exchanging routing information over the MPLS domain. Right, so these two routers are exchanging routing information across the MPLS domain while at the same time being separate from other customer routes. Okay, and that means, so there's the network over here and the customer networks on both sides, and because of the routing protocol that is exchanging domains, we can send traffic to the other side, and everything in the MPLS domain is hidden. Right? If you were to do a trace route, it would it'd be like boop, one hop, boop. Okay, this would look like one hop, and these would look like they were, well, actually, it would look like this: hop, 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 hop. Okay. All right. And of course, the different customers are isolated. Okay, so the provider edge routers are going to need to use VRF instances so that the customers and their traffic are separate. There's a separate VRF for each customer. All right, and then the appropriate interfaces are associated with the needed VRF. Customer edge router and provider edge router are going to exchange routes using some routing protocol. It could be interior or exterior. All right. Then those routes that are exchanged, okay, that's going to exchange routes, are placed in a customer specific VRF table on each provider edge router. Okay. But from the customer's perspective, that's just a customer controlled router. I should say from each of these routers perspective, that's just another router of the network. Now the administrators know it's not. They can't get in there and configure that, right? So these, gosh, I hate it when it does that. Come on. Okay. So these are going to exchange routes. Then those are going to exchange routes using, which I'm kind of getting ahead of myself, but BGP. So provider edge router and provider edge router have a TCP connection, right? So these are kind of hidden as far as the routes are the exchanged routes, and then those routes are exchanged with each other. All right. So all right. So essentially, if you were to look at the routing table or the routers, if you looked at OSPF or EAGRP, the customer routers would see these routers. Like customer B would see those, right? And then customer A would see these in their topology. OSPF might be the best example because you can see all of the routers in the OSPF table. Okay, but all of these routers are hidden from the customer. They don't see those. All right. So once the provider edge routers learn the routes from the customer edge routers, the provider edge routers are going to redistribute those routes into multi-protocol BGP. And just to make things complicated, we usually just say BGP. Okay. All BGP these days is multi-protocol BGP. So I like to point that out because the book starts calling this MP BGP, whereas it's always MP BGP. So it's just the provider edge routers are going to talk directly to each other because they have a TCP connection to exchange the routes. Okay. So the routes go here, multi-protocol BGP goes over here, multi-protocol BGP. Okay. And then that is the TCP connection. Along here, we're still dealing with MPLS where we're going to add a label. All right. So again, a BGP is unaware of the whole label thing here. BGP is creating a TCP segment, putting it into a packet, sending it on its way directly to that router. And but MPLS is handling all of the stuff in the middle there. Okay. So the provider routers in the middle are not participating in BGP, only the provider edge routers. Again, they're talking directly via BGP. All right. And of course, we're using iBGP because those two routers are in the same autonomous system. All right. So we're exchanging the routes using whatever, routing protocols that the customer is using. Or I'm sorry, this is actually we're going to have an interior routing protocol in this domain. It's usually OSPF or ISIS in most cases, because traditionally for years and years and years, EIGRP was proprietary. So service providers used ISIS or OSPF, even though now EIGRP is now opened up. But service providers, they have decades old networks using OSPF or ISIS. They're not going to switch over to EIGRP at this point. Um, so the PE or the provider edge routers and the customer edge routers are going to use the customer dynamic routing protocol to learn about all the destinations in the provider network. Okay, so I'm sorry, the provider edge routers and the provider. I think I said customer. So the provider edge routers and the provider routers are going to use the dynamic routing protocol to learn about all the destinations. All right. The PE route, provider edge routers, are the only ones using IBGP on top of that to exchange the customer routes. Okay, so let me just restate this. Okay, the service provider is using OSPF ISIS to advertise all of its internal networks. Okay, then MPLS is built on top of that to create label switched paths. Okay, now switching gears. The customers are exchanging routes with the provider edge network. Um, and then that's going to exchange over here. Well, that leg of it is going to be done via IBGP. The IBGP packets are going to be carried across the network via MPLS. And those MPLS switched paths are going to be built based on the information shared here between all the PE routers and the PE routers. Okay. Hopefully that kind of breaks it down. So inside the ISP, we've got a dynamic routing protocol, advertising everything. Then we have MPLS. That is going to create label switch paths, and that's the dynamic ones. The specific paths here could be manually created, right? So say customer B has another site over here, all right, and we get to another network, all right. So we may decide to manually create this tunnel for whatever reason, or maybe we know this router is going to go out or whatever, so we're going to manually create the tunnel like that. So these MPLS tunnels inside the MPLS domain of the provider network, more often than not, are actually manually provisioned, even though they can be created using dynamic routing protocols. Okay. All right. So the question: what are advantages of MPLS layer 3 VPNs? Okay. Advantages versus what? Like layer 2 MPLS VPNs, or like what are we comparing it to? Advantages? What do you mean? Versus just having a service provider network of just OSPF, for example. In this example, I mean, I guess we could back it up. Why use MPLS at all? And the reason is because it can carry lots of different kinds of traffic. So we're talking about a layer 3 VPN, okay, where if we did a trace route from the customer network, you've got those hops. A layer 2, whoops, well, that's bigger, yeah. A layer 2 VPN, it would look like this. And these would be hidden. There's a reason to do a layer 2 VPN and a reason to do a layer 3 VPN. Okay. So let's back up even further. I have a branch office. Oh, let's see. Well, I've got several branch offices. Okay. And we have the whole world. Now I'm going to get a layer 2 VPN. And basically what that means is it's, according to my equipment, it's 1,000-mile long Ethernet cable. Okay. So I'm going to do a layer 2. So I got branch 1, branch 2, branch 3, branch 4. Okay. All right, well, I'm going to do another layer 2 view, but these need to be connected. So I want to, do kind of like that. And then I need these to be connected, and then it's just kind of like, no, you know what? Why don't we do something else? Instead of doing a layer 2 VPN, because now we're getting complicated, and, like this would be okay. A layer 2 VPN would be okay if we had 1, 2, 3. Okay, they're all connected eventually somehow, not super efficiently. But when you start getting a lot of branch offices, layer 2 VPNs start not being super helpful. So you want to switch over to a layer 3. All right, but now that is you get into some routing situations. All right, so now this example, it doesn't line exactly with the example in the slides that we're talking about, but it's the concept that I want to point out to you. What if this became just like a giant ISP router, right? You were plugged into here, plugged into here, plugged into here, plugged into here, and um, and we exchanged routes with the ISP giant router. Well, now, let's say we want to send traffic from branch 1 to branch 4. Okay, we send it to the ISP router, and it knows where to send it. We want to send traffic back. We want branch 2 to talk to branch 4. Well, just send it to the ISP router, and it can get it there. That is the benefit of the layer 3 VPN. This is where, now, it's not a giant ISP VPN, router, right? We happen to know that, there's a router here and a router here and a router here and a router here. Okay. And we are exchanging routes. Okay. And then, regardless of what's going on in the middle, we don't care. These service provider routers create these MPLS tunnels to get traffic where it needs to go. Whoops. It's going to create these tunnels, right? So now branch 1 has a MPLS tunnel to all 3. Now again, imagine you had another dozen branches, or 2 dozen, or 3 dozen branches. Now you start to see the benefit of a layer 3 VPN. And this is why we exchange routes with the edge of our service provider. And now, we don't care what path is being taken in the middle. It's all invisible to us. We just know, it just looks like all of our branches are directly connected at layer 3. Okay. So, branch 1 sends a packet to this router. It makes a routing decision because we exchanged routes with the service provider, and it knows to send it wherever it needs to go. And that way we don't have to have 500 layer 2 VPN connections. We essentially, the ISP becomes a giant, it's like the ISP network is our network. Except it's not, right? We have a virtual network laid across the top of the service provider network, along with the traffic of lots of other customers. That was a good question, because I'm not sure I would have gotten into that if you wouldn't ask that. So good job. Did I answer your question? Now that I'm awesome. Okay. So let's see, where were we? Okay. So what if customers are using the same private IP space? Okay. So if all the customer routes are being redistributed into BGP, how does BGP handle the overlapping prefixes for customers? And the answer is a route distinguisher. Okay. That takes the customer's IP prefix and gets added to it. So now that there's a unique combination, all right, we are now distinguishing these routes from other identical prefixes. So the route distinguisher is created by the provider edge routers on a per VRF basis. The customer doesn't create them. Okay. And then the provider edge routers are going to create a route distinguisher even if the IP space isn't overlapping. So the route distinguisher is 64 bits. It gets added to the 32-bit prefix that's being advertised. Same thing with IPv6, just adjust the numbers. Okay. So that's going to create a 96-bit unique prefix called a VPN v4 address. Actually, I take that back for IPv6. There is route distinguishers, except there's not there. You don't have the concept of private IP space, so that's different. Sorry. Almost everything between IPv4 and IPv6 is the same here, but not that part. All right, so we have a VPN v4 address, which are exchanged by iBGP neighbors, right? The provider edge routers. Okay. Now, we might use an AS number, but if we're using private IP space, we're probably going to use that in the example that we are given. Okay. So in this example, we're just doing like AS1 with a VPN identifier of 100. Okay. Added to the 32-bit route itself. Okay. So in this example, they don't have overlapping space, but if those IPs were the same, let's say this was 10, we could tell them apart by the route distinguisher. Okay. Oh, I guess customer A adds the 10 dot space, so these two are then different. The 10 dot space is used by both customers. Okay. So basically that gives us the VPN label and the MPLS label, right? So VPN label and the LDP label, the label distribution protocol, the MPLS main label. All right. And so the VPN label is just to distinguish overlapping IP spaces for BGP, right? So this is BGP, this is MPLS. Okay. So a packet arrives at the ingress provider edge router, and it's going to attach both labels, the MPLS label, the LDP, and then it's going to do the route distinguisher for BGP. Okay. The egress label is going to use the VPN label to determine which customer this is for and what should be done with it. All right. And it learns that from BGP, from iBGP. Okay. Then the MPLS label, the LDP, the label distribution protocol label, is used for the actual label switching from provider edge to provider edge and everything in the middle. Okay. And of course, that is figured out using label discovery protocol that we talked about earlier. Okay. So here we have provider edge 5 router. Okay. Is going to learn the 10.0.0.2 from customer edge router B. Okay, I'm actually going to switch colors here. Okay. So provider edge router 5 learns about this 10.0.2 network from customer edge router B. Going to place it into customer B's VRF instance, all right, and redistributes it into BGP. And we have a VPN v4 route of 110, 10.0.0, or 10.0.20, okay, which also needs its own label. So for MPLS purposes, that's going to get label 35, okay. This gets shared with provider edge router 1 via iBGP. So if provider edge router 1 up here receives a packet for that network, it knows to attach label 35 and send it on its way. This is known only by the provider edge routers, okay? So if provider edge router 1 forwards a packet to provider edge router 2 directly, it's going to get dropped, okay? Because provider edge router 2 has no idea what 35 means. All right, so this label needs to, the label distribution protocol label is needed to forward the packet all the way over, okay? I know there's a lot of moving parts to this. Again, I just want to make you feel better and just say you don't have to be an expert at this. You're not going to have to know how to configure it or know any commands. All right. So just do your best as to just kind of have a rough understanding of what MPLS is. All right. Any questions or anything? That's basically it, by the way. So it looks like I was right in the middle of my hour to an hour and a half estimate, so not too bad. We're at about 1:15, I think, or maybe 1:10. All right.